coded messages have, throughout history, been really important for communication. Yes. Okay. Yes. Well, I would probably do the same if I do Canvas, I think. Yeah. Okay. That's great. Thanks. So throughout history, sending secret messages has been important. Even long ago, the way that you send secret messages would be different. But in many wars, it has really been really important. So if we just use numbers for the letters, that's a really poor code. So I'm going to show you a way that matrices can be used to encrypt messages, and it's pretty cool, I think. And it was actually used a lot at some points. Now, I must add this in. Computers have really changed the game on encryption because we're going to use matrices to encrypt a message here, and I'm going to show you how it would be, to me, really difficult to figure out this message without knowing what the encryption matrix is. However, computers can figure it out pretty easily. So if you can program a computer, so this encryption is very basic in the world of encryption. So if you're talking like, like bank information, high-level security, like the Pentagon is not using this method anymore. They may have long ago when things were on paper, but I do not understand or even know much about the levels of encryption that are used in computer ages to keep data safe. So that is beyond this. But this sort of gets you started in that direction. The other thing I have to tell you is that we're going to look at inverse matrices, but only of a 2x2 matrix. Inverse matrices also become much more complicated whenever your matrices are bigger. So you could go a lot further with this, but I think it's a pretty cool little thing to study to kind of give you like an introduction to where you could go with this stuff. So, so if we have a coded message like here, the crow flies at midnight, you could take the letters and change them to numbers just like I did on the warm-up, right? So T is going to be 20, H is 8, and so on. All right, so I've already done that here. I've changed these to numbers. So you could then choose an encryption matrix, right? So you can make that up. It could be anything. There's a few certain things you don't want to use because they will, like you wouldn't want to use a matrix full of zeros. Use the matrix full of zeros, everything would just turn out to be 0, right? So that would be a bad idea. It would be okay, I think, to have like one number that's a 0, but you would not want them all to be zeros, I think. Even though, I hope that's true. I'll put a 0 in one of these. Oh, I didn't change that. We're going to change that when I get there. Actually, let's go ahead and change it right now. On the third message there, let's change this matrix because I forgot to change it where I copied and pasted. Let's make it -2, 4, 1, -1. On that third matrix there, for the message number 3, change that encryption matrix there to -2, 4, 1, -1. Okay. All right, let's go back. All right, so here is what you can do. You come up with an encryption matrix. It just needs to be a 2x2 matrix. Then you are going to put your message into a 2x(n) matrix. N depends on how many letters you have in your message. So in this case, there were, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There were 26 letters. And spaces count as zeros. So there were 26 characters in this message. So I did a 2x13 matrix. So that had 26 spaces. If you had an odd number, you would just, like if we had 27, then we would do 2 by 14 and just let your last entry be a 0, a space to end it there. We've got this here. So if we take our encryption matrix and multiply it by our message matrix, it gives us this matrix here. I've done it for you on this first problem just so you can kind of see what's happening. So let's do this. Let's now put the numbers for each place here so we can kind of see what they're corresponding to. So we got 59, 16, 11, 20, 6, 49, 39, 50, 14, 21, 31, 26, 30, 79, 24, 16, 20, 9, 67, 54, 73, 14, 27, 43, 35, 35. So I wanted us to do that, like to show where they correspond, because I want you to see how difficult this would be to decode if you had no computers or if you were just trying to figure it out. So if I had just given you this string of numbers for the warm-up and said that we intercepted this message, look at how difficult this would be to figure out. You got no correspondence with the order of the letters in the alphabet. T is at 59. E is 11. Those are, there's not even 59 letters in the alphabet. But here's what's craziest about it. Look at all your spaces right here. Right here, this space is 20. This one's 14. This one's 24. And this one's 9. So you don't have a single letter corresponding to something there. You can see, like here, this T is 20, which was the same as this space right here. But this T over here is 35. Right here you got 35, 35 for the H and the T. So you could see if you were given this, I think if I had given you this, or even if I'd given you the word Desmos, but I had coded it this way, where the two S's were not the same, it would have been really hard to decode that there. So it makes a much better code. But the key to this is whoever you are sending the message to must know what your encryption matrix was. Because if they do not, they cannot decode the message. So let's look at how we decode a message. So the person who is receiving your message would have to know what your encryption matrix is, and they would have to know how to find an inverse matrix. Inverses are things that undo each other, right? The inverse of addition is subtraction. The inverse of multiplication is division. So the inverse of multiplying by the matrix A, B, C, D is multiplying by this crazy matrix right here. Okay? So let's use this to do an example here. So we're going to take this encryption matrix and we're going to find its inverse. So the inverse we denote with that -1 there, so this would be the inverse of matrix E. And so if you have your letters in this order, A, B, C, D, so that would mean this is A, B, C, D, then you're going to find 1 over AD minus BC. This has a name. It's called the discriminant of the matrix. And it has several uses, and I can't remember even some of them, but it is something we talked about a lot in linear algebra, I remember. So for that discriminant, we're going to do 1 over A times D, so in that case that's 2 times 1 minus B times C, so that's 1 times 3. And then for our matrix, we've got to switch the A and D. So that would put a 1 here and a 2 here. And then we're going to leave B and C where they're at, but we're going to make both of them negative. So this 1 right here would be a negative 1, and this 3 right here would be a negative 3. And so if we do that here, we're going to have 1 over 2 minus 3, so that's going to give us a negative 1 times 1, negative 1, negative 3, 2. So our inverse matrix here would be negative 1, positive 1, positive 3, and negative 2. So grab your calculators. You'll need those. All right, so I want to just, I already know what this message is, but I want to decrypt it to make sure that it's working correctly. So I'm going to enter my matrix here, this C matrix, the coded matrix. So I'm going to enter that in A. So it is a 2 by 13 matrix, and let's hope I can get all the numbers in right. So that's this 59, 16, 11, 20. That's what you'll be entering. C, the one that starts with 59, 16, 11, 26. So I got all those in there, right? Okay, so you're going to have that 2 by 13 matrix in. Then you go back to the matrix menu. So second, x to the negative 1. You're going to go over to edit. Make sure you put this in B, or you're going to erase all of the work that you just did for A. So in B, I'm going to put my decryption matrix, that inverse matrix there, which was negative 1, 1, 3, negative 2. Okay, so if we go back to the main screen now, if I multiply the inverse matrix by the coded message, it has to go in that order because you got a 2 by 2 by times a 2 by 13. You can't switch the order on those. You can't multiply them. So we'll do B times, not that, A. Here, it's going to give us this matrix, which if I go back up here, should be the same, I believe it is, as the one that we had in the beginning. So now you've got the letters, and you can just turn the letters back in, the numbers for the letters, and you just turn those back in. So once you decode it, you could just use this chart here. 20 is T, 8 is H, 5 is E, 0 is space. So you could turn those letters back into your letters there. Or you could turn your numbers back into the letters there. So I think this is so cool. I realize that you have to be even smarter than this if you're like working at the CIA and having high-level security. They got to be just like crazy geniuses. But I think this is so cool because it is a kind of like neat application. We can pretend like if we were spies in the 1900s, early 1900s, that we would be working on stuff like this. So let's look at doing one ourselves. So if we have math is fun here, we are going to use that. I should have put that so you didn't have to flip back and forth constantly. But we're going to use that code for our letters. And so we've got, we'll count spaces as characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've got 11 spaces. So we need to make that 12. So it's going to be, we're going to do a 2 by 6 matrix, and we'll just put a 0 as our last one since we don't have 12 numbers. So for our message matrix, the M is 13, the A is 1, T is 20, H is 8, we'll put a 0 for the space, I is 9, that's 1, 2, 3, 4, 5, 6 numbers, so I'm going to go down to the next line. So 9, and then S is 19, put another 0 for a space, and then F 6, U is 21, and N is 14. We're really done here, but we're just going to put a 0 there for the space to fill out the matrix. You can't leave a blank space there. Okay, so they give us the encryption matrix right here. So I'm going to go ahead and encrypt my matrix. So, or encrypt my message here. So I'm going to do matrix, edit. Let's do a 2 by 2 for our encryption matrix here. So that would be 2, negative 1, 1, 3. And then we need to put our message matrix in another matrix, so I'm going to put that one in B. So that would be 2, 6, oh. Alright, so that 2, negative 1, 1, 3, we put that in as A. We put the message matrix in B. You can put it in as any letter. It doesn't really matter. And then we're going to go back to the home screen, clear everything out. And we need to do A times matrix B. And so our encoded message would be 7 to 34, negative 5, negative 1, not 1, 14, 18, and then bottom line 71, 38, 71, 42. Everybody okay encrypting the message? But especially if you're sending a really important high-level message, you probably want to double check you did everything right before you send the message. Especially since if you think about doing this in the 1800s or 1900s, early 1900s, you did not have a calculator. In fact, this like nifty TI-89 that could do matrices, that's pretty recent when you're looking at major human history. So you were multiplying these matrices by hand, and we went over how to multiply matrices. It's not the easiest, right? It takes a little while. So you would probably want to check to make sure that you got it right before you send the message. So if we were going to do our decryption matrix, it would have to be 1 over, and then it's A times D, which is this diagonal, so 2 times 3, minus the other diagonal, B times C, so 1 times negative 1. And then for the matrix, we're going to switch our A and D, so that'd be a 3 here and a 2 here. B and C stay where they're at, but we change their sign, so we'll have negative 1 and a positive 1. Now this is going to end up being 1/7 times 3, 1, negative 1, 2. So our decryption matrix is 3/7, 1/7, negative 1/7, and 2/7. So let's put that. I wonder if I can. Let's see if this will work. Store matrix. Let's see if that worked. I hope it did, because that'll save us some time here. Oh, it does. Okay, so when you're doing these problems, you can store that coded. So you should still have that coded message 7234 negative 5. That should still be there on your screen. So if you will hit this button right here, we've used it to store things as variables before. Store, and then tell it, go to the matrix menu and tell it C. It will store that as your coded matrix there in C. That way you don't have to type it in to check to make sure it's working. Right. So now all we have to type in is our decryption matrix. So I'm going to put that in D. Here's a good thing about these. You can put in 3 divided by 7. It'll change it to a decimal when you do that, but you don't have to divide it and get the decimal first. So you can just type in 1 divided by 7 there for that point, negative 1 divided by 7, and 2 divided by 7.